Hello, everyone. I'm John Erkoyuncu. I'm based at Cranfield University. And today I'd like to give you an update, really, in terms of the digital twin demonstrator that we're developing as part of Transit. So this is called the East Midlands Air Freight and Road Deliveries demonstrator. And we're working together on this demonstrator with colleagues at Heriot-Watt University and University of Glasgow. So this EPSRC funded program. So just to go into more detail, so the context that we're looking at is East Midlands, where we're trying to combine road transportation and air transportation. And the core question for us is, how do we enable decarbonisation? And the digital twin here is looking at across transport domains. How do we provide feedback back into systems so that we can start to design and also deliver these transport networks? So there are a number of challenges that we're looking at. So firstly, we're trying to reduce emissions. Secondly, we're trying to optimize investments in terms of how do we electrify? How do we maybe move into SAF or other types of approaches? And how do we enable resilience as well in terms of sustaining the optimized carbon footprint? We also want to look at lowering costs so that this is done in a trade-off sense. And we're also considering the business innovation in terms of whether there are new business models that can be developed. So the types of requirements that we have, we've got various partners such as DHL involved, and we're trying to understand things like electrification of fleet. How do we start to manage energy from an infrastructure point of view? Where will the charging facilities be? What sort of facilities, infrastructure will we need? All those kind of questions we're trying to optimize. And we're also looking at efficiency and resilience from a transport perspective. And a big part also of the project is really looking at data in terms of how we can move towards automation of data integration. So we're defining digital twinning as an approach. And in that, for us, it considers the integration of models, shadows, and twins. And the way we're building the demonstrator, it's about integrating the models and the shadows and the twinning in that respect. So, so what I'll show you today is a bit on the infrastructure, the architecture in terms of how we'll manage the data, and we'll show you some illustration of how the model development has taken place. So in terms of the digital twin framework, we're using and kind of aligning to the standard ISO 23247. And in there, we're defining user entities, core entities, a data collection procedure, and we're also defining the observable manufacturing elements. So we're also looking at the cross-system entity as we're looking across different transport modes. And in this process, we're trying to build connections between different data, different models, and tackle interoperability challenges as well, so that the digital twin can evolve over time and represent the complex environment that it's looking at. So, so just to go into a bit more detail, so for us, the conceptual model involves firstly the physical space where we're defining the observable elements like vehicles, different products, the equipment like forklift, infrastructure could be road. We're defining all the different observable elements. We have the network layer, which is connecting between the physical and the virtual space. So things like sensors or edge computing, and the setting interface, which links the virtual space. And in the virtual space, we're looking at different types of models, different types of decisions that we're trying to make. And we're also thinking of how we engage with different users. So it could be dashboards, AR, VR, could be various maybe text-based messages that we share back. And then the next layer is looking at cybersecurity. So in there, we're looking at things like data transmission, the data assurance and the security support aspects as well. So it's this is really the basis of how we're enabling the digital twin to operate. So in terms of the insights that we're trying to gather, here you can see we've broken it down based on what the model can do, what the digital shadow can do, and what the twin can do. So in the model, we're looking at how do we simulate logistics, the fleet operations. In terms of predictive aspects, we're looking at energy demand. From an optimization perspective, we're looking at the trade-off between cost and power. And we're ultimately trying to analyze the decarbonization approaches. In the digital shadow, we're looking at the fleet in terms of how do we analyze the fleet, how do we start to optimize the operations of the fleet, and we're also trying to optimize the energy use and emission intensity. So we're monitoring and trying to capture real-time data or right-time data in that context. Digital twin side is more in terms of how do we start to have autonomy in terms of providing feedback into the transportation in terms of energy, emission management, and we're trying to look at the range from 1 PL to 5 PL, and again, trying to define what does autonomous features look like. So the simulation that we've been building has particularly been looking at the fleet, looking at the energy side, looking at assessment in terms of how do we start to move towards resilience, how do we start to trade off between emissions and cost. And we're also looking at different types of technologies like electrification or SAF or other approaches. We're trying to trade off between all these approaches in this process. So we're using ontologies to manage the data side and to facilitate the interoperability. And in this process, we've used many existing architectures. We've adapted these. So the LOT OSIS methodology has been adopted in this process, and we're trying to align to developed approaches and things like fairness and consistency is critical from our side in terms of how we build the ontology. So this just goes into a bit more detail where we're defining ontologies for different transport modes. So you can see we have air, road, maritime, rail represented in the program. And we're trying to define a reference ontology through the transit program. And from there, we've got a standard IES4 for the information exchange standard. And then we're also looking at the industrial ontology foundry. And at the top level, we're looking at the basic formal ontology as our overall architecture. So that's giving us a more consistent way to formalize data and to formalize relationships between data. So this slide I won't go into too much detail, but this is how we've developed the ontology for the digital twin. And this is a more UML class representation of an agent-based representation of air and road in this process. So this is really giving us a very structured way to define different types of data input that we need for the digital twinning. And it's also giving us a framework to be able to access the data from different sources. So just to close off, we've built a simulation, and I'll just play that. So this is looking at how do we integrate air and road transportation. And in this process, we've got an agent-based model. We're using a software called AnyLogic. And here we're able to connect the data automatically to the model and start to have a dynamic representation of different road and air illustrations. So in this process, we're using the model to be able to optimize the carbon footprint, and we're looking at also the trade-off between cost and carbon. So our next steps, and you can see here the different movements and different sort of transportation mechanisms can be represented. So just to close off, our next steps will very much focus on the feedback mechanisms and trying to tackle interoperability at a large sort of sense so that we can connect any data and any model to have a comprehensive representation. So with that, thank you very much and look forward to questions later. Thank you.
So John, our first question to you, please, is pleased to see that you're using the ontology to help integrate disparate data from multiple sources. What are your key lessons from this work?
Great, thank you for the question. I mean, I think firstly, trying to define the purpose at the top level is key so that you can scope what the sort of data range is. I think for me, that's one. I think the other thing is, it's quite easy to get lost in different data terminologies. So I think mapping those building taxonomies is important, but you can spend a lot of time, and we need to balance that pretty much in terms of how much time you're investing in developing that. So I think the key thing here is how do we generate value? How do we get some benefits along the way rather than waiting to be completing everything?
I have two questions here, John, for yourself, which are first more technical in nature, and the second at the bottom of the screen here as well, both to do with the ontology. So I'll ask the bottom question and then supplement it with the more technical question, just because of the time we have. So a brief, concise response, and the author can speak to you offline to follow it up. Are you using the ontology to drive real-time visualization? Do you have a utilization? Do you have to utilize this to perform in a particular way to achieve the performance, if I can say the wording?
Yes,
and also
absolutely.
there's a second question there around how the interface with IES and BFO.
Yeah, perfect. Thank you. Really, really good question. Thank you. So I think for us, we do want to move towards real time. And the way we're doing this is trying to create interface, a connector approach between the ontology, the different data sources, and the simulation. So you could see this as there's a bridge in the middle that we're creating that facilitates any data to be connected to any model. And that's the methodology that we're trying to focus on developing as part of this. I think in terms of the second question, I fully agree with this comment. It's really tricky to connect these. I think the reason we're looking at connecting these is that, yes, there's merits in both approaches. And I agree, like there's a 3D and 4D, a mix of 4D approaches considered. I think the way we see interoperability is that we should be able to connect any data to any model and vice versa. And in that process, we need to think about how do we enable flexibility. So in some cases, we'll have a BFO approach, some cases, IES. So for us, we also see a connector-based approach is what we're trying to develop. So this doesn't exist, and that's exactly what we're working on at the moment, so that we can connect these two methodologies and these structures. And it is proving challenging. I can confirm that. But for us, we see that it will actually lead to a lot more, let's say, broader connectivity and a lot more interoperability if we can tackle this gap between the two approaches.